We now talk about motional EMF. So this is the EMF which is induced in a conductor moving through a constant magnetic field. So motional EMF comes due to motion. So let us consider a particular instance of this. So you consider a straight conductor of length L sliding across two fixed parallel conductors. So this is the figure. So this is the straight conductor of length L, as you can see, and it is sliding across these two parallel conductors with velocity v. The magnetic field is constant and is applied perpendicular to the plane of the circuit. So magnetic field is constant and is applied perpendicular to the plane of the circuit. So you see the magnetic field is going into the screen. So going into the screen. And you can see that this straight conductor is sliding across with the velocity v. Now this sliding will change this area. So you have this area of a rectangle. So this area keeps changing. So at any instance, there is a very small change in area. So this is the small change in area at any given instance in time. So say if this small distance is dx, so this small distance is dx, then the small area would be, this area would be L times dx. So L is the length of this yellow bar times this small width dx. So this is the small change in area. So the flux formula is given as, you know, integral of magnetic field dot product with the small area vector. Now we have already seen that the magnetic field is constant and applied perpendicular to the plane of the circuit. So this expression now becomes B dA cos theta, and cos theta is 1 because theta is 90 degrees. So this is nothing but B, and this LDX is dA. So we plugged LDX in here, and B and L are not changing as the bar is sliding. So magnetic field is constant, the length of the conductor is constant, so BL comes out. You just have integral of dx, for which we get x. Now notice that the formula for EMF was E was equal to minus d phi b by dt. So this flux we calculate as BLX. So you put in BLX here, BL and are constant, so they come out. You just get dx by dt. So this dx by dt is the velocity v. So notice this x is nothing but the distance which this rod has already slided. So x is the distance at which, or the distance which the rod has already slided through. So this is the distance x. So dx by dt is nothing but the velocity. Now suppose the circuit has resistance R. So we have already put a resistance R here. Now if the circuit has resistance R, we know that Vi is equal to R. Now V is nothing but the EMF here. So this EMF we replace by this absolute value of EMF times I is equal to R. So just copy the formula down, and from here you can calculate the value of the current. You just plug in this absolute value of E as BLV. So we are ignoring the negative sign here. So this is nothing but BLV, and this is how you get the value of the current flowing through the circuit. Notice that current has a particular direction. Now this direction we will learn from Lenz's law. Now we consider another example. So say there is a metallic rod of length R. So this is the metallic rod of length R. So one end is at the center, the other end is at a circle. And the magnetic field B is again perpendicular to both this metallic ring. So this is the metallic ring and this metallic rod. So again the cross sign means that the magnetic field is going into the screen. So the small change in area, so now this is the small change in area. So basically this rod is hinged at the center and the other end is at the metallic ring. So as in the figure, hinged at the center, other end is at the metallic ring. Magnetic field is perpendicular to the plane of the ring, and this rod is, say, revolving. So say it is revolving in this direction. So this was this initial position, this is its final position. So the small change in area is this small area of this sector. So this is the area of the sector, is the small change in the position. So this small area, so this dA vector, so this area of a sector is given as r square d theta by 2. So this is the area of the sector, this is the angle. So if you have a circle like this and this was the sector, so you need to know first the angle. If the angle here was phi, then the area of this sector would be r square phi by 2. So that is the area of the sector. So you have the small change in area. Again you have B vector dot dA vector. This becomes B dA cos theta. Now again we have said the magnetic field is perpendicular. So this cos theta becomes 1. So you just have B dA. So this is B and this is our dA. So now you just integrate over the entire theta. So you get B r square theta by 2. Now this EMF, so again I'm taking absolute value here. So therefore I've dropped the negative sign. So for the absolute value of EMF we have d phi b by dt. So we are just copying this here but taking absolute value, so dropping the negative sign. So magnetic field is constant, radius of the rod is constant, it comes out, 2 is constant, so you just get d theta by dt. Now d theta by dt you denote as angular velocity, so you put omega there. So the EMF here in such a setup is b r square omega by